All right. Um, so yeah, I've got 235 here, so I'm gonna get started. This is COMP2404 Introduction to Software Engineering, and I'm Daryl Hill, the instructor. So hopefully you guys all get your assignment 1 in. I didn't get many. I usually get way more emails the night before an assignment is due, so that's encouraging. Today is the 6th. We're going to look at UML class diagrams. Before we do that, I'm going to discuss a little bit about assignment 2, which is not actually due till after the break. And tutorial 4 is out, and I think tutorial 5 will get released automatically this weekend, or maybe I'll move it up. This is basically a bunch of stuff about arrays. So all the different types of arrays, just so you know how to use them, syntactically. And then this is, it actually does some, again, it's unit tests for assignment 2, and it has to do with deep copies and memory management, which is a lot of what we're going to be doing in assignment 2. But yeah, any questions on the calendar before we get started? Yeah. Let me think about that. Probably not, but I mean, they're not that hard to come up with, and you can get them from other students. I just don't want officials. I'm going to use some variation of it next semester, and I don't want official solutions floating around out there. But I'll think about it. I don't know. I might change it up completely. So other questions? Okay. So last class we were talking about essentially what our new, what our applications are going to start looking like, and that is we're breaking them down into control objects and entity objects and collection and view. So it's a lot like model view controller. And to that end, I introduced this list class, and we went through a few things. So in assignment 2, you're expected to, I think I call it an array class in the assignment spec. But essentially, you're going to be expected to take this and adapt it to use to store photos and photo albums, right? So it's a photo album application, of course, just a fake one because we're still sort of new to all this. But so before we get into that, let's talk about what assignment 2 looks like. And I'm going to draw sort of a UML diagram, a very rough one, which is kind of apropos because we're going to talk about UML diagrams today. So assignment 2 is, again, very similar in structure to assignment 1 in terms of we're going to have classes that contain collections of other classes. So this is photogram because I'm not very good with names. So it's a photo application for, I guess, storing and viewing photos. So in this, I'm going to have a, so I typically would draw this as an array, right? But I'm not going to do that anymore. We're going to go more into UML style diagrams. So your photogram app will have a bunch of albums. And how we represent that is with the star. The star means 0 to many. Okay, so this is beginning of UML. We're going to get into a lot more detail later in the class, but just a little light look at it here. And then our album has a bunch of photos. So I can draw it like this. And the photo has name, date, and things like that. So we can put a date here as well. And yeah, so that's about it. Nothing too complicated. The trick is, so, this photogram application stores a bunch of albums. I can add, remove them, delete, things that we've been doing up until now. The albums will store a bunch of photos, and I can add, remove, and delete those. And at that point, what we're going to do is introduce another sort of control object So imagine you have a phone and it runs some sort of client application. And then in my client application, what I can do is I can store a bunch of photo albums as well. And I can, in some sense, download them from the main app, which is just going to be, you're going to be making a deep copy of these. And then when I delete them from the main app, they should still exist in the client. And so, any combination of adding, deleting, and whatnot should not cause a memory leak and should not cause a double free and should not cause weird behavior, well, any of the weird things that can happen when you mess up with memory in C++. Okay, so it's going to look a lot like that. There's going to be a lot of things repeated between the client and the main application, but it's just to practice that deep copy. And then there's going to be, of course, a couple of test classes, a view class and a test control class, and that's going to be your assignment too. All right, so hopefully you got, I don't think it's too difficult to conceptualize, but any questions on that? Okay. Because yeah, I do get, and fair enough, I do get people saying that, well, when I read the specification, I really don't get a sense of what this thing does until I get like halfway through writing it, and then they start to realize. So I want to sort of arm you with the overview before we get started. So not shown here is the array classes or the list classes that we're going to use or you're going to make. But these are implied here, right? So when I have this one-to-many relationship from client to album, that means I'm going to store a bunch of albums, and it's going to be using some sort of data structure that we're going to do. We're going to implement ourselves. Okay. The other change that I want to make is, so I said we were going to practice with double pointers and return parameters or output parameters. So in this case, if I wanted to get a student, I pass in a double pointer and an index or a name, and I get back the student. But for the purposes, I mean, I was sort of reviewing it. For the purposes of the assignment, I think we're going to go with return values, simply because almost every single, I don't know any data structures that use return output parameters. So we're going to go with return values, which means you can take this code and modify it. It's not that difficult. But instead of having a double pointer, we're just going to return a student pointer, and then we're going to do null checks on it to make sure that it's valid data. Okay, so we're going to change that a little bit. I think having getters that use double pointers is a bit overkill. So yeah, the first thing let's do is I'm just going to show you how easy it is to modify this. So if I have my get here, for instance, I'm still going to pass in a name parameter, but I'm going to return a student pointer. Okay, and that's it. And it's actually much easier and a lot more, it's actually a lot more elegant to use. Double pointers can be awkward at times. Okay, and then the remove will do the same thing. When we remove, we want to return the thing we remove so that whoever is, calling this remove function can decide what to do with it. So the exact same thing. Now we can just return a pointer, much more straightforward. The add can stay the same, although I do ask you to add according to index. All right. So now if we look at the implementation, we will fix these errors that we get now. So stu is now a return value. Oops. Okay, and then all this is going to be, so here I return true. Well, I can just return, oh, yeah, boy, this touchpad is really sensitive. So I'm just going to return the, once I find the correct element, whereas the name is equal to the name of that student, then I can just simply return it. And if I happen to go through the entire list of students and I don't find the student I'm looking for, I can just return null pointer if you prefer. This is probably probably better to use this null to be more consistent with the test cases, but here. Again, quite simple. Instead of assigning it to the output parameter, I'm just going to return it. And here, this will change to null. Yep. As far as I know, I mean, I don't know. I would have to look it up actually to see what the difference is between the capital nulls and the null pointer. I'll get back to you next class with that, because yeah, I'm not precisely sure. I think this is sort of maybe the old style, and maybe null pointer does something a little more, because I do see null pointer more in modern C++, but so yeah, I'll look that up for next time. Remove, this one's a little more complex. But not super complex. So in the place of false, I'm just going to return null. That's what we're going to check. Here I still have to save the student here, because I don't want to return him yet. I want to first, overwrite that position by copying over the elements. And then down here, I can return stu. So yeah, a couple of small changes, and we have basically some working code here. What did I do wrong here? Yeah, so functionally it's almost the same, but or functionally it is the same. We're just using return values, which are sort of a better fit for this stuff. Okay. Something else I was going to show you. Oh yes. So the other thing. So in the university, in my list class, actually, I have a remove up to, which is the bonus question on your assignment 1, something similar to that, right? So on assignment 1, you had to remove up to as defined by the less than function. So basically, I look at all my reservations, and all of the ones that are in the past, I want to delete those. So I'm going to do the same thing here, except I'm going to just do it by remove up to the student name. This is not a particularly useful function in this context, but just so you have a blueprint in the future for how to implement this. So yeah, let's just really quickly before so what I want to do is I have an array of students in sorted order. A, B, C, D, E, F, and I want to remove up to, let's say, D. So I want to remove all of the students up to D, or, it doesn't have to be a student that even exists in the list. I can just test using the less than function. So what I'm going to do is, well, I'm going to, in some sense, delete all these, but not really. I'm just going to copy E and F down to the front. All right, so that's what remove up to should accomplish. And to do that, I'll keep track of the index. So I'm just going to walk through my list until from the beginning to the end until I find a name that is, what do I want to say, less than or greater than. Yeah, a name that's greater than this name. Okay, so while and perhaps I just walk off the end of the list. Okay, so if what did I call it here? Elements, perhaps, yes, elements. Okay, so I'm comparing the name that I passed in. I'm checking to see if it's less than the current name. And if it is, then I've gone far enough. If it's still greater than the current name or equal to in this case, then I want to keep moving. So in this case, I will break. I found the correct location. Otherwise, I will increment my index and I'll continue the loop. At which point, I'm going to say, I'm going to define remove is equal to index. So I'm going to keep incrementing index, and remove just keeps track of how many locations I'm trying to delete. And then I will continue my while loop. All right, so then elements, oops. At index minus remove, right? So in the first iteration is going to be, since I'm subtracting a thing from itself, it's going to be 0. So location 0 is going to get whatever is at the current index, right? Which is what I wanted to do. In the example before, index was equal to the position of, well, we just passed D, so it would be at the position of E, and we're copying that into the first location. And we're going to keep going until we get to the end of the list. So okay. Oh, the other thing I wanted to do is add these elements to array. Right, so all the ones I remove, I'm going to return using this output parameter. This should be index. Okay, and so what you would have done on assignment 1 is something very similar. You wouldn't be comparing names, you would be using overlaps and less than, maybe just less than. But in principle, it would be the same thing. I'm going to look until I find up to the element I'm supposed to remove. I'm going to keep track of how many elements I'm going to remove, and I'm just going to copy them back that many, right? So if I have to remove 3, I want to take whatever's at element 4 and move it to position 0. And whatever's at 5, move it to position 1. Whatever's at 6, move it to position 2, etc. All right, questions on that? Okay. Anybody, how many people got the bonus? 2, yeah, okay, yeah, I don't think it's that hard, but, and there's of course other ways to do it, but this is one way. I don't know if I'm set up to test this, let's try. Oh, yeah. All right. Well, because I changed my list class, I would have to go through and adjust a bunch of stuff. Maybe not that many. Okay, so I can add a bunch of students. B, 2, 2. Okay, so remove up to student, student number. So remove up to, let's say, 2. There are print all students. And it didn't work. All right. All right. I'm not going to fix this. It's possible. I think there's a few things I have to update in order to get this working, but so yeah, I'll have this working next class and we can test it out. For now, I will move on to UML diagrams. But yeah, any questions on that before we go? All right. So part of software engineering is documentation, and we're not going to get into all of the documentation in this class. We're going to basically focus in on UML class diagrams. So UML class diagrams is sort of introduced in assignment 2 in the sense that I give you a UML class diagram that sort of similar to the picture we just saw actually, but a lot more detail that shows you how this thing goes together. And then for some of the questions, some of the specification, I just say, well, refer to the UML diagram so that you can get used to reading them. And then in assignment 3, you're going to write one based on the code that you write. So yeah, we're going to, on assignment 3, when you make your UML diagram, you will refer to these slides. This is the official UML specification that we're going to be using. There's a bunch of different specifications out there, and I'm not really, well, we'll talk about that as we go. All right, so first we're going to start talking about documentation in general, the different types and the purposes, and then we're going to zero in on class diagrams. Again, there's a bunch of other documentation, but you're going to be taking that in 3004. So yeah, the purpose of this section is to introduce class diagrams. So when we're writing a program, there's many types. Yeah, I basically just told you all of this. So yes, I know people who work at Google, and when they describe their work week, it is something like this. They code something up, their manager or whoever asks them to write some code. They write it, it takes them one day. And they go back to the manager and say, I'm finished. And the manager says, okay, I need you to write some tests for that code. So they go, okay, and then Tuesday, they write all the tests, and then they come back and they say, well, I've written a bunch of tests, and the manager says, well, write some more tests. That's not enough. So they end up doing about 2 days of tests, and then once they're done that, they come back and their manager says, okay, now document everything that you just did. So document your code and your tests, and then they do 2 days of that, and that's basically their week. 1 week, 1 day of writing code, and then 4 days of basically making sure that code is up to standard. So yeah, why is documentation so important? Well, one of the reasons, I don't know if you've ever tried using a language or a library that had subpar documentation. It's crazy. So I've had a couple of experiences with that. One, there was plenty of documentation, but it was not consistent. There was a couple of versions of the language out, and so I wasn't really sure which one I should be using, and it wasn't really, it gave you examples, but it didn't explain what was happening. And another one was a library I used for C++. Had no documentation. Like, how are you supposed to figure out how to use it if there's no instruction somewhere? So those are interesting experiences. I wouldn't recommend them. It's a lot of guesswork, trial and error. You got to write code, you got to output it and see what's actually happening when you call a function, once you figure out what the functions are. So if you contrast that with a language like Java, I mean, you can say what you want about Java, but the documentation is fantastic, right? I can Google any Java anything and I get Java docs. This documenting utility is built right into it. So you can compile it using a special kind of comment. That's fantastic. And this is sort of the experience you should want to give other developers. You don't want to write a bunch of code that only you know how to use. That's not really useful. Yeah, so you give that experience to other developers or yourself. If you've ever written anything large enough and then, took some time off, a couple months, and then came back to it and tried to figure out what you were doing, that's always an interesting experience. The other thing is, maybe there's a superstar at your job, they're the lead programmer. people hop jobs a lot in this industry. So the person that was sort of hands-on with all of the details of the application is now suddenly gone. And what do you do if you're, maybe you just came on and you're learning, and then nobody knows how to finish the product. So yeah, ongoing documentation is important. So in general, our software development lifecycle, we start with a requirements analysis, right? You want to figure out what you're building. You talk to your client, ask them questions, figure out what they want and what you can actually do for them, inside of what they want. And then you design it, you make a plan for, it can be sort of vague or very, very detailed depending on where you work. Yeah, a lot of places are, sit down and code and document as you go, and other places are, well, let's make a big plan first and then work from there. But yeah, I like to code as you go, but then you implement it. So after you have a plan or a general idea of what you're doing, you're going to start writing code. And then once you have code, you're going to test it. All right. So this is basically somewhat of a software development life cycle that you will see. Different parts are emphasized depending on where you work, but and each of these requires separate documentation. So the requirements analysis, this is the huge, depending on who you take it with, 3004, but you have we had to make a 60-page manual before we even wrote code. Did not like that. Some people like documentation. I like coding. But there are some useful things in there. So functional requirements, what does your application do, or what is it supposed to do? So this is, on assignment 1, when we did the tests, you ran the tests, test everything, get your mark. That's based on functional requirements, right? Things that I asked for this code to be able to do. Then there's non-functional requirements. In the context of developing code, this is things like, well, if I make a query, it should return within 5 seconds, something like that. We have sort of our version of that where I asked you to use, for instance, statically allocated arrays, right? So these are expectations I have that are not quite, I don't define what the code's doing, but how you should get there, some of the surrounding properties that you should have. User visible constraints on the system is the official way, but use cases. I like use cases for figuring out what you're doing, right? So it's sort of easy to have an idea in your head. It's a little more difficult to go through that step by step and say, well, the user sits down, now what happens, right? Okay, so they click, they double click on the icon, and then what comes up? Is it a login screen? Is it a welcome screen? Is it a loading screen? What should be happening? And then what do they do next? So these detailed use cases are very useful for hammering out, I thought I would be able to do it like this, but it turns out I'm going to need a whole other web page or whatever. High-level object model. So you want a high-level, basically the objects you're using in your application, you're going to model them similar to what I just sort of showed you at a very rough level about assignment 2, but yeah, model the interactions of the objects in your application. Basically the major objects. You don't really need every single detail, but you want to have a good idea of what's happening. And then the dynamic model is the system behavior over time. These are sort of like flow charts, perhaps, or swim diagrams they're called. So they model the interaction of your different objects. All right, so yeah. So in addition to that, we have our design step. So we have a subsystem decomposition, right? So you're going to divide your application into subsystems and talk about how they interact. This would be, sort of the model view controller would be one way to do it. A detailed object model. So then you're going to object all these subsystems with the objects that should go into them. When you're doing implementation, your documentation, program comments, intelligent naming conventions, tutorials, things like that. I really think in some cases, you can get away. You can tell a lot of the story by using good naming conventions, right? So you tell a lot of the story of what's happening in your code by just giving good function names and things like that. It used to be sort of the old style C was everything was a contraction or some weird name that didn't make any sense. And so you really had to be on the ball. But now that we have more memory, we can actually name things with expanded names, right? Back in the day, that was because you only had so much memory, so they had to shorten everything. But now we can actually tell the full story. So testing, test plan, and test cases. They each have their own documentation. So yeah, code should be self-documenting whenever possible. Should read like a story. That's the ideal, of course. Takes practice to get there, or sometimes, depending on the code, it's impossible to get there. But keeping functions and classes with simple single purposes and appropriate names helps, right? So get price with tax, I know what that does, right? Maybe I don't know every single detail, but I got a good idea. So that's self-documenting. You could still add additional comments, but yeah. And again, I'm not marking comments in this class because it tends to be very inconsistent. You get some TAs who just, if you get 10 marks for comments, they just give you 10. And then other TAs go through and they give you 0. So it's very difficult to get consistent marking. So just try and make your code readable. But yeah, when you make classes in the real world, you should actually document what that class does. How to use it, the purpose, and any complex or critical, right? If it's a data structure, you should say, well, these operations will run in what time, like linear time, log n times, things like that. All right, test cases. So should describe what portion of the program you're testing, the input and the expected output. So that's sort of, I think I sort of give you that. Maybe not every single detail here in the tests that I've given, but you know, that should be the goal. Unit tests are usually pass fail. Integration and system testing, they're more complex. So in assignment 2, there's some automated testing, but then there's some that is manual testing. So you can inspect the code, and the TAs are going to inspect the code when they run it. As our applications get more complex, it's harder to unit test. You have to build a lot of infrastructure to properly test. And then if you do your print statement a different way, then maybe it fails for no reason. So there's going to be a lot more manual marking as we go. This part gets more complex. All right, so UML is one of the documenting tools. It's the unified modeling language used during the design phase, right? So, and specifically, it's to help document object-oriented design. Yeah, so one thing to keep in mind when you're writing your UML diagrams is it's a communication tool. It's not we have a specification for a reason, because when I write something, you're not sure what it is, you can refer to the specification, but it is a communication tool. It's not about being right or wrong, it's about getting the ideas across, right? So you should keep that in mind when you're wondering, oh, can I do this? Should I do that? Well, is it ambiguous, or is it clear what you're trying to communicate? Programming language independent, right? So UML technically can be implemented in any object-oriented language. In reality, you will see certain artifacts from certain languages. It's just the way it goes. Okay, so types of UML diagrams, we have class diagrams. So that's the main one we're going to be concerned with. So these model the attributes and operations. So these are the members of your class, the member variables and the member functions, and the associations between classes, right? This is composition or uses or things like that. Activity diagrams and sequence diagrams model the behavior of the program. So we're going to see an example of a sequence diagram, but basically, Does this object pass a message or call a function on another object? State machines. So a lot of our applications do have state. They're not just state machines, but parts of it can be modeled as state machines. So, yeah. So activity diagrams not shown here, but if you've ever seen a flow chart, you know, yes, no, some question, and then a branch. That's basically an activity diagram. It's a flow chart. Models the behavior of your class. This here is a sequence diagram. So this gives a timeline of when functions are in use, their life cycle, and when they communicate. And you can sort of see here implicitly the function call stack, right? So here would be, you know, the main function, not really the main function, but whatever the launch function is in my main object. And then I make a call to concrete builder, and that goes on the function call stack. And then it returns back here. And then I make a call here, and then it returns back here. So I can trace what the code should be doing, the messages that are being passed, how it operates. Yeah. This would probably be something I would do after I've written the code, not maybe before, I don't know, but yeah. And then you can, you know, have a little X here that says, well, after this point, this object is deleted. All right. State machines. If you don't know what a state machine is, then something like a soda machine would be a state machine. Back in the old days when you could, I guess you could still put coins in them, but I think that's sort of not happening very much anymore. But you start in a state of 0 cents, and then depending on which coin you insert, this machine enters a different state. Right? So I insert 10 cents. It goes to the state that, okay, I have 10 cents. From there, I can insert either 5 cents or 10 cents. If I insert 5 cents, it goes to this state. And then there is a end state, right? So at some point I get 25 cents and I dispense my drink. That's a state machine. What's that? Ancient times, yes. What are they now, $2 or something? Yeah, well, I didn't want to draw a huge state machine, but yes. Once upon a time, you could get this for a quarter. I could age myself here. Yeah, I used to get 50 cents to go buy pop and chips when I went bowling on Saturdays as a kid. And that would give me 1 pop, 1 chip. And but the tax was extra, so that's it. Jeez. Anyway, all right. So one example of this where the state would be integrated is, you know, if you're in a stealth game, one state might be the enemies have seen you and they're aware of you and they're chasing you. Another state might be the enemies are not aware. So it's not like the entire game is a state machine, but it does have aspects of that. So the behavior of the enemies depends on the state in this case. All right, so that all brings us to UML class diagrams, which is the main focus of this class, the documentation in this class. So these slides are considered your specification. So when you ask, what do I do in this case, refer to the slides. If it's not here in the slides, you can either ask me or you can use your common sense, right? So if it's not specified, then you won't get deducted, right? But I do think I specify everything here. So UML class diagrams model the classes and the associations between the classes. All right, so our classes consist of attributes. So this is a generic term for instance variables or data members. Instance variables of Java, data members are C++. So that would be, these would be our attributes, right? So we're keeping track of data. The operations in UML, operations are the generic term for member functions or methods, right? So score goal would be an operation here. The access specifiers are represented, right? So we have private is the minus, the hash mark is protected, and the plus sign is public, right? So, and we said it's independent of your programming language, but of course, protected means something different in Java and C++. So it's hard to get away from a programming language completely, but all right. So when we make a class diagram, so this is a hockey game class. So we make a square with 3 sections. So the top section is the class name. The middle section is the attributes. So these are the member variables of our class. Sort of, I guess, kind of the opposite of what we do in our class specification. And then the operations are the last thing. All right. And it's not like C++ where we divide it by public and private. I can have public anywhere or private anywhere. So I have a public operation and 2 private attributes here. If the class is abstract, we use italics. So the class name is the name of the class. We'll talk about abstract classes. I mean, in general, they are just basically classes with abstract functions. And an abstract function means I've defined a function interface, but I haven't defined any sort of implementation for it. We'll get into that later. So yeah, the syntax. So when I make an attribute or a member variable, I start with the access modifier. So in this case, I start with the minus sign, followed by the attribute name. So now in this case, the name is important. It doesn't have to be the variable name, but it should be, this is a communication tool, right? So I want this to be a meaningful name. So home in context of a hockey game means something. All right, and then followed by a colon and followed by the type. So yeah, it's a little weird, a little awkward, I guess, at first. It's just I don't know. It's another thing you have to learn. But yeah, that's the member variables. Yeah, so here's an example of an abstract class in italics, right? So this means it has 1 or more abstract functions, which are not shown here, but if I have a static data member that's underlined, we haven't gotten to static members yet, but it's basically something that's associated with the class instead of specific objects. In C++, there's something called friendship. All right, so friendship we don't show. There's a bunch of stuff in UML diagrams that we just don't show because it's not useful in this context. So friendship associations are never shown. These are specific to C++, not object-oriented in general. Yeah, so my operations now, these are my member functions in C++. So yeah, everything in here would be a operation. Again, I start with the access modifier, so private, protected, or public, followed by the operation name. So here I make a line. A line is just basically 5 people who go out on the ice at the same time. Yeah, and then after that, followed by the parameters in commas, or sorry, separated by commas. Parameters in parentheses, separated by commas. All right, so this is basically a function name and the parameters. So here we mark them as input parameters, output parameters, or in-out parameters. Right, so here we have in-out, which means that basically I'm giving you some information in, and then you're going to modify that object and use it as a return parameter. Or if it's just input, I just put in, or if it's just output, I get rid of that. Yeah, if it's just output, I just put out. So that means I'm returning a player. And then followed by the colon again, and followed by the return type. So if my add player returns a Boolean, I put a colon in a Boolean. If I don't have any return type, that I assume it returns void, right? So if it has a return type, you need the return type. If it doesn't, if it has a void return type, then you can leave it off. Okay. Yeah. All right. So this is the part I think that's a little bit sort of awkward compared to what you've been doing so far when you're programming. But anyway, any questions so far? All right. So in addition to the classes themselves, we're going to model the associations between classes. So there's the two main relationships. There's composition and inheritance. There's also a uses, which I included in the assignment 2 UML. You don't have to put that in your assignment 3, but well, I'll describe it in a little bit. But composition is a HAZA relationship. So in this case, my hockey game class contains a team class. Right, so we've seen this thus far using, what did we see it with? Wild University contained a student, you know, and in your hotels contain the rooms, and rooms contain the reservations. So that is a HAZA relationship. So the container is the class that contains an instance of another class, and the containee is the class contained within the other class. So when we're writing this out, we have a couple, so we'll get to this example in a sec. So the characteristics of composition, we represent composition with a line, possibly some numbers or symbols, and possibly some arrows. Okay, so what does that all mean? Well, we want the direction of this composition. So which class contains which? So if there's only one class that contains the other, then I'm going to put an arrow. But if, you know, if my hockey game contains a hockey team and my hockey team contains a bunch of hockey games, then I don't need any arrows. I just use the line. We'll go over that again, but so unidirectional, if class A contains one or more instances of class B, then I use an arrow, right? So I have class A contains class B like this, and then how many I will mark at the end of that arrow. If it's bidirectional, class A contains one or more instances of class B and class A is contained. Class B contains one or more instances of class A, then that's bidirectional. They each contain each other, so we use a line. We indicate the multiplicity. This is the number of containee instances possible in the container, right? So I have to go through whatever the range is. When we had reservations, you would have either 1 or 2 dates, depending on how you implemented it, right? So you'd put 1 or 2, whatever you did there. Of course, when it came to the room, you could have 0 reservations up to whatever it was, 256. In that case, you could just write 0 ... star. That means 0 to many. Or you could just write this. Essentially, that means the same thing. Or if you have to have at least 1, then you should write 1 ... many. If I need at least 1, but I can have as many more of those as I want, then I need to specify that. This multiplicity only applies to composition, never to inheritance. All right. Okay, so composition in this case. I would have a all right. I'm almost certainly under arrest by the I don't know, for some tax evading or something. Whatever. I usually like wasting their time because they get really, sometimes you can make them really angry. It's fun. But yeah. All right. So in this case, I have a hockey league is my object, and it contains a schedule. It has exactly 1 schedule. So hockey league contains the schedule. The schedule does not contain any reference to hockey league. My schedule contains 1 to many hockey games, right? So once I make the schedule, I add hockey games. A schedule can't exist without at least 1 game. That's pointless. My hockey game contains 2 hockey teams in this case, and my hockey team also contains a bunch of hockey games. So the hockey team contains 0 to many games, and each game consists of exactly 2 hockey teams. Since each of them owns an instance of another, we don't put arrows on this line, but we still put the multiplicity. A hockey team has 5 or more players. Probably should be 6 or more. And the hockey players belong to exactly 1 team. Right, so that's sort of how that would be laid out in this case for composition. All right. So we always require the multiplicity. The arrows depend on, you will almost always use arrows in yours. I think I really try to avoid this in our applications because it's a bit tricky with the make files. All right, questions? Yeah. Many. Yeah, so in this case, I have 5 ... many. It means I have at least 5 players up to as many as, yeah. Yeah, so exactly. So this and this mean the same thing. Yeah. Other questions? All right. Now, again, this is this specification. I've taken the most general elements of UML diagrams. You might see slightly different specifications out there. In fact, you almost certainly would, depending on what you look at. So important convention, we do not explicitly show collection classes, right? So these are all implied using the multiplicity. So if I have in my university, I had a list of students, I do not put that I have a list of students. I would write it like this. Right, so that's it. University contains 0 to many students. When we wrote this, there was a list class, but I do not put that in. It's a collection object. That's a decision I make at implementation time. I know I need a collection object, but which one I use, I figure out later. Yeah, another example, a library contains many books. Maybe we have a book array class. That will not appear in the UML diagram. It's just a collection class. We don't model it at this level. Yeah, they're not important for design, just for implementation. The other thing, inheritance, that we're going to get to. So this is an is-a relationship. I'm certain, almost certain you guys have seen it in 1406. But I can have a more general class would be considered the parent or grandparent or ancestor, also known as the superclass. And then I can get more specific. So a person has a name and an age, and maybe I print the stats. Maybe they have a contract. But I can get more specific and say, well, a person can also be a player, and then I can add on more attributes there, right? So that's the nature of inheritance, is I take something that's very general and I add more specific things to it. So in this case, the player would be known as the subclass, or sometimes the child or grandchild or descendant in general. All right. So when I'm writing inheritance in the UML, I use the triangle, the open triangle. It points to the superclass. So I have an NHL employee, and a hockey player is an NHL employee, and a defenseman is a hockey player and also is an NHL employee. I can also have coaches, assistant coach, and head coach. And so I get this type hierarchy where the superclass is pointed to by the triangle. All right. I think we're almost done this. So in this case, when we're using inheritance, so I have an abstract class here because of this abstract function, right? So the italics makes the function abstract. So when I inherit from the person class and my player class, I'll leave it up to you whether or not you want to represent this, right? So we have to override the print stats function in the player class in order for it to be a concrete class. But whether or not you show it, again, UML diagrams are about communication. So does it communicate what you're trying to communicate? You should sort of consider that. Yeah. We will accept either for the assignment. You can include them or not include them. It's up to you. All right. Other things that we don't show in a UML diagram: constructors and destructors. Do not show them. Getters and setters. I don't show them. I don't care. They're sort of very low level stuff. And collection classes. The other thing, the common mistake is that when I'm showing composition between objects, so when I write my hockey game, if I have primitive members, I put those in and we put strings in with the primitives. Okay, so if it's a string, we're going to write it within our hockey game class. But hockey game also contains, in this case, 2 team objects, but I do not write them in with the member variables. I represent them using the UML diagram. All right, so that's important. If I had a student that had an address, I would represent it like this, and not like this. All right. Questions on UML? Yep. So inheritance is very, very specific. This is composition, right? So this is my hockey game contains 2 team objects. Whereas when I inherit something, I would I write it as so class person, and then I say, for instance, public. If I inherit from animal, let's say. So now it's actually quite different from, well, ostensibly it's very different from composition. When you get behind the scenes, it's pretty similar, but yeah. So yeah, you should, composition and inheritance are 2 different things as far as we're concerned. So yeah, in this case, I have a person, player inheriting from person, but a team is not a hockey game, right? It's not is a relationship. So yeah. Right. Other questions? All right. So when you're making your UML for assignment 3, we introduce it here because I'm going to start using it to show you, basically before we go into our little examples. I might model it with UML, so I want you guys to know what we're doing. But when you're doing this for assignment 3, draw.io is a great UML modeling editor, but you can use whatever you want. I don't care. Submit it as a PDF. No hand drawn, please. But draw.io is available anywhere. You can use it from your browser, or you can download it from Windows Store, Software Center, or Mac. I don't know. I don't have a Mac, so I'm not sure where you would get that. I'm sure if you go to the, I forget what the website's called, but if you Google draw.io, it'll take you there, and you could probably find something. If you want to install it on the VM, install Snap, which I think it's already pre-installed on the VM, so you can just open a terminal and type that in, and it'll install draw.io. Okay. All right, so that's UML, the fascinating world of documentation. And yeah, so we will come back to that from time to time to model things, but and then for assignment 3. So now we're moving on to encapsulation. So your assignment 2, again, we're getting very into the detailed memory model. So memory is very important in assignment 2. A little bit of UML, a little bit of documentation, a little bit of separating out our collection objects, right? So we're going to use I think I call it photo array and album array as sort of an abstraction layer between our classes and the raw arrays. But the other very important thing in assignment 2 is encapsulation. All right, so encapsulation, we're going to talk about in great detail, and there's various things involved here. But one of the main things is the const. Right, so assignment 2, a bunch of people every semester. I mean, I need to take out a billboard, I think, sometimes, but so you're going to be applying const to your functions, to your members, to your parameters, anywhere where it's appropriate. And if you don't, you're going to lose marks. So, you know, I'll remind you again, and we'll talk about what exactly that means, but it does tend to get ignored at this point. So when we talk about encapsulation, we'll talk about composition. So encapsulation is basically, you know, when I'm hiding implementation details, part of my implementation details are the objects that I'm using. So we're going to talk about composition, and then we'll talk about constants, which is, you know, the big place where everybody seems to lose marks on assignment 2. And then we'll talk about friendship, which is, you know, C++. Their philosophy is, you know, here's all the tools you can use to make good software, and then, you know, here's all the rules, and here's how you break them. So friendship is breaking this encapsulation contract, but sometimes it's necessary. And then we'll talk about static class members. Okay, so composition is when an object contains a member variable that it's an instance of another class. As we talked about, when we model it in UML, we should model it these as 2 separate objects, not as, I should not have an address variable here, even though I do have that in my student class. So yes, primitives I would write here, but objects I write as independent entities. And this is has a relationship where the container contains the containee, and the containee can be statically or dynamically allocated. Again, that's an implementation decision, not really a design decision. So on initialization, the container initializes the containee. It calls the constructor either implicitly or explicitly. So these are objects contained with objects. Every object, when it's made, has its constructor called. These are no exception. The question is, when does it get called and how do we initialize it? So what we use, or one of the things we can use, is member initializer syntax. So as we'll see, it's a little tricky to get a hold of that object, that member variable, before it gets initialized. So we use a very special syntax that gives us access to it before its constructor is called, so that we can pass in arguments. Yeah. So this helps us avoid creating temporary objects, as we will see. So the example we're going to look at, we have a student, and a student, of course, has an address. So we can store all of these member variables in our student class. That's, of course, fine, but it's bad design, especially if we have an address class available to use. So what we want to do is reuse code whenever possible, which means that, you know, we're going to reuse the address. So when I make a student object, I'm actually hiding the fact that I'm using an address, right? So I'm just going to take in all of the address parameters and construct that object myself. And then if I change my implementation later on, I don't have to change my interface. All right, so the constructor includes the address parameters, and then I supply these to the address class. And then I should do other things too, like I want to print my student. I want to print their address, but address probably knows how to print itself better, right? So it has all of the, you know, somebody already implemented it, so we should take advantage of that. And this gives us proper encapsulation. Student class lets the address class do its thing. How the address is initialized is up to address. How it prints is up to the address. We have, even within the student class, proper encapsulation. All right, so we're going to look at composition, and we're going to look at how we would actually initialize the address class. We'll We'll give a couple of bad examples, but then we'll look at the good way. All right. So the main problem is when we have a student and an address contained in it, the address constructor is called first. So how do we supply its arguments? All right, so I have to. Okay. Okay. So we have here our address class, which is, yeah, it takes in a number, a street name, a city, and I believe a province. See, I should have named them. Yeah, so a province. So this, again, this is sort of why we use, or why I like to use, you don't need to have names here for your variables, but it can help, right? When I'm looking at this address constructor, what is this string? Why is it different from this string? Well, if I put the names in there, they're not necessary, but it makes it more readable. So yeah, street number, street name, city, province. Okay, so in my constructor, I announce that I'm in the address constructor and I initialize all the member variables. This is pretty standard. When I'm in the destructor, I announce that I'm in the destructor and I have a print function that, very simple print function. Now in my student class, I have all of my student arguments, right? So I have a student number, a student name, the major program and the GPA. And then I also pass in the address arguments. So I have a street number, a street name, a city, and a province. And I just have some default values there. So in my main function, I make a student. I pass in a bunch of address information and student information, and then I print it out. But let's just see what happens when we do that. Okay, so I'm making a new student, and then we can see here that the address constructor gets called first, and then my student constructor gets called. And then I print out my student. The address is not initialized because I didn't initialize it. And then when I'm exiting the main function, my student is destroyed, followed by my address. Okay, so then the question is, how do I initialize my address? Yep. Yep. In the student constructor? So what would happen if I didn't provide default arguments? Yeah, I mean, that's what's happening now because I haven't initialized address. Yeah, so let's take a stab at initializing it and see what happens. So I've initialized the number, my student number, student name, major program, then GPA. But what do I do with address? So it's called address. No, wait, what's it called? Home address. Okay, so maybe I want to think I should do something like NSCP. Okay, so I want to initialize it somehow, but this doesn't work. So I want to call the constructor, but the constructor's been called before the student constructor's been called. So this is no good. One thing I could do though is I could take advantage of my assignment operator. I can make a temporary address variable. I initialize it and I simply assign it to home address. So this doesn't call on the constructor explicitly. This calls on the assignment operator, but it's going to work, at least in terms of initializing this thing. Let's take a look. Nope. All right. So I have now the address constructor is called twice because I made a temporary address object in my student constructor. And then the destructor of that temporary object is called right away. However, when I do print out my student, the address does print out. So this does initialize that address member variable, but it's inefficient because, of course, I make a pointless, in some sense, temporary address object. Yeah. Does that make sense? Any questions on that? Okay. So this works, but we're taking advantage of this assignment operator, and it's not really what it's meant to do. So what we want to do is we want to grab this address, right? The address constructor is called before the student constructor, so I can't initialize it in this body here. Whatever I do is going to be inefficient. So I want to grab it before the body. So we use what's called the member initializer syntax, which is pretty long here, but so I'm going to put a colon here, and then I can grab home address. What I tried to do before, when I tried to pass in these arguments, I can do that exactly here. Home address, whoops. And then I can pass in number, street, city, province. And I can get rid of this. Okay, so what am I doing? Before even the body of this constructor is called, it grabs this home address and it supplies these arguments to its constructor. All right, so we'll see now when we run our code that only one address constructor is called. Right, so we have an address constructor called, and then when we print out our student, we have all of the proper member variables, and then the student is destroyed and the address is destroyed after. But we did not have to make a temporary object. This got initialized right away. All right. So, yeah. Questions? All right, we got about 7 minutes. I'll show you another couple things about this. So what if this worked before because, well, one specific reason, because I had a default constructor. If I take out that default constructor, then all of a sudden you see this is lighting up. The compiler is mad at me because, well, let's see, what does it say? No default constructor exists for the class address. Right, so if I don't initialize it using this member initializer syntax, it's going to look for the default constructor, and if it can't find one, it's going to complain. However, if I do put this back in, number, street, city, province. So even if I don't have a default constructor in this case, what's it complaining about? Oh, yes. Now it's complaining because of my copy constructor. But even if I don't have a default constructor, I can use this member initializer syntax to initialize an object contained in another object. Okay. And of course, it's complaining here. It also wants a default constructor, but I can do no, home address is yes, stu.home address, sorry. Okay, so in my copy constructor now, I also want to initialize this home address, object, but I'm going to call on the home address copy constructor. So I could try and, say student.homeaddress.number.name, blah, 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 but the home address knows how to initialize itself, initialize a copy of itself. So I'm just going to ask it to do that. Okay, so that keeps the encapsulation. I don't need to know too much of home address's business. As a student, I simply say, please make me an address object. I call print when I need to. I make a copy when I need to, etc. This we don't need anymore. Okay. Questions? Okay, so the interesting thing about this is that I can use it for anything. You see here, I've used it for an object, but I could use it for strings. I can use it for floats. I can use it for any sort of primitive. So I can say, oops. And you'll see this quite often in C++. If I want to initialize my number, so this is my student number, and I'm going to initialize it using this parameter. They're both called number, and this looks sort of funny. So I'm saying number, but what it is the first number is the parameter or the member variable of my student class, and this one is my parameter. Right? So then I can do that for all of my student major program. And set it, oh, GPA. GPA is just G. All right, so I'm really running out of space here, but yeah, so I can initialize all of my member variables using this member initializer syntax. Yeah, strings, primitives, even pointers, which we'll show you in a bit. But yeah, make sure this still works. Yeah, so my student, everything gets initialized. The number, the name, the program, all using member initializer syntax. So what you see often in C++ is I might see a constructor that has an empty body. Everything's been initialized using this member initializer syntax. That's perfectly normal and perfectly okay. Yeah. Okay. All right. Questions? Yep.
How was the address connected to the student exactly? Like, is it in the student.h?
Yeah, it's in yeah. It's just it's a member variable. So yeah. Again, in UML, I would represent this separately, but inside the class, it's all packed together with the other member variables. Yeah, other questions? Yep. Exactly. We want more details about it. Yeah. So, and to represent those more details, we need a separate box, basically. Yeah. I'm not sure exactly what you mean, but
but instead of it being like it's the grade for each course, so if you use the member initializer, if you have to put like all the values in there and initialize it that way.
I think you could do that. I've not tried it, but I think you could. You might have to put it in curly braces. Yeah. We could try that maybe next class. We're running out of time today, but yeah, I like that question. I like questions like that because yeah, probably, but I'm not sure. All right. Any other questions? All right. So that's it for today. We'll pick up next class with encapsulation and